So we can use the.
Sorry for the disturbance.
Yeah.
Just started
So,
recording.
Actually, for the chemical characterization and all, so we can use the XRF also for the to know the chemical composition, X-ray fluorescence spectroscopy, and also we can use the ICP-OS, which is the inductively coupled plasma optical emission spectroscopy, and also GDOS. So these techniques we can use to obtain the elements and also composition of the elements. So within the material or the alloys. So we can also do the microstructure characterization, so which involves using the optical microscope, SEM, TEM, EPMA, and also structural characterization techniques like XRD and small and wide angle X-ray scattering techniques. So mechanical characterization techniques such as even from the beginning to hardness, and also tensile test, fatigue, creep, fracture toughness, impact testing. So all we can do, which gives the complete metal characterization. Especially in this talk, I'm going to present on the microstructural characterization techniques. So both microstructural as well as the structural characterization techniques. So my outline of the talk is as follows, where actually I will give the introduction to the metal characterization techniques, basics and their applications. So as I mentioned, so these are the optical microscopy, scanning electron microscopy, transmission electron microscopy, electron probe microanalyzer. So which are the microstructural characterization techniques, and TM also we can use for the structural crystal structure determination, and structural characterization techniques like crystal structure determination and all. So we can do using the X-ray diffraction and the small and wide angle X-ray scattering techniques. So then I will present how I have used these characterization techniques so in research and development activities. So one such example, so I will present on how I established the structure property processing correlations in metastable beta analysis. And also I will give one more example, so how I have used all these characterization techniques so to find out the metallurgical failure analysis or to find the cause for the failure. So one such example, I will give the microstructural characterization of the failed valve gear of the aero engine. Yeah, it is not moving slide.
No, sir. The slide now we are seeing is outline of talks.
Yes, madam. Yeah. Okay, now it is not moving further.
No, sir.
It is not moving. Yeah, 1 minute. It's not moving. Okay. Now it is moving. Yeah. You can minimize this one. You can minimize this. Madam, 1 minute. Yeah.
Yes, sir.
You can see. No friends. Okay, no problem. Let it be there. At the top only. Okay. With this or this also? Huh? No, actually, I want the title there. Previous slide. Yes. This one, I want to close this one. Leave this one. No, okay. I want to close this. It's not leave. No. 1 minute. It's not going. This one or this one? Yeah. Screen will click करके forward move कर. Oh, okay. Line. Click and then Yeah. Yeah, I'm sorry for the interruption. So now actually I'll give the introduction to the metal catalytic techniques, basics, and also their applications. So now I'm talking about these microscopes, scanning electron microscopes, and TM and all. So why should we go for microscope? If you see that, so if you see the human eye, so the resolution is around only 0.1 mm. So what does that mean? Suppose the distance between 2 points which are shown here are the two lines. If the distance two lines are more than or equal to 0.1 mm, then only human eye it can resolve that these 2 points as a two separate points are the two lines. If it is less than 0.1 mm, so at least you can see using the magnifying glasses where you can get some kind of details. If you want to go the further finer details, now I have to go to the microscope. So which is the stereo microscope. Okay, basically stereo microscope is a variant of the optical microscope which is designed for the low magnification observation of a sample. So this also uses the reflected light. So where actually in the stereo microscope, so we can see the three-dimensional field because it uses the two separate optical paths with two objectives and eyepieces to provide slightly different viewing angles to the left and right eyes. So this arrangement produces a three-dimensional visualization of the sample being examined. So because of a large working distance, even at low magnification, so that is useful for the examining the larger objects. So there is no sample size limitation. Suppose this is one actual drive pan pinion, so which has failed. You can see that some of the features are here. So this one directly I can keep under the stereo microscope and I can get the image like this, where you can see that some kind of the lines are there. Okay, that I'm not able to see with the naked eye. So using the stereo microscope, where you can see that these lines are very clear. So these lines are basically the beach marks. So which indicates that this has failed by the fatigue. Suppose if you want to see details within this, are the microstructures in this drive pan pinion. Now I have to go for the optical microscope and the scanning electron microscope. So basically, so if you see the optical microscope, so which creates an magnified image of an object specimen with an object lens and magnifies the image furthermore with an eyepiece to allow the user to observe it by the naked eye. If you see that actually in the optical microscope, we are able to see the microstructure because these metals are opaque and they can be viewed under an optical microscope only under the reflected light. If you see here, so there is the light source which is having the suppose if you see the ordinary visible light which is having the wavelength of the 500 nanometers, which will this light rays it will pass through the condensers and all, and then so we have the semi-silver glass plate, so which will reflect these rays towards the objectives and then it will fall on the specimen. After interacting with the specimen, again these rays will reflect back, it will pass through the objectives and then pass through the semi-silver glass plate, and then finally you can see the microstructure, this kind of the microstructures. So where you can see that this is the grain boundary. So grain boundary you are able to see as a dark. So because these if you see that no light is reflected from the grooves that form along the grain boundaries, so and they appear as the network of the dark lines under the microscope, and basically these grain bonds are selectively affected by the etchant as they process the higher energy. These grain bonds process the higher energy than the interiors. So this is the optical microscope. Whatever this is the schematic, and this is the photograph of the optical microscope where you can you can keep your sample here under the lenses, and light will come from here. And these are the eyepieces. You can see the what is the microstructure, and on screen also you can see. So actually, the resolution of optical microscope is around the 500 nanometers. So where you can see that wavelength of ordinary light is around 500 nanometers, and resolution also should be approximately to that of the wavelength of the light. It should be around 500 nanometers. But with the nowadays with the technology in the lenses and all, so by using the oil immersion objective lenses, you can get the resolution up to 200 nanometers and all. See, actually now I will explain the some of the terms they used in the optical microscope where so resolution is very important. I'm talking about the resolution. Actually, the main goal of the microscope is actually to get the enlarged pictures of the object with the best possible resolution. Suppose if I'm taking the high magnification image, if the resolution is not good, suppose if the image is blurring, so there is no use. That's what actually the resolution is very important. So resolution in the like optical microscope, you can get suppose delta, which is the resolution, so 0.5 lambda by mu sin alpha, where is lambda is the wavelength of the illumination. and mu is the refractive index, and alpha is the half of the cone angle. So this mu sin alpha, it is also called the numerical aperture. So if you see that these mu, especially in the object lenses and all these lenses, so it will be maybe 1.5 to 1.7 you can use. That is the refractive index of some of the lenses. And this we will also talk about the magnification. The total magnification will be given by the power of objective and power of the eyepiece. And generally in the optical microscope, the useful magnification range is you can go up to 50 to 1000x. And also, what are the other terms we can use? So that is the depth of field, so which is defined as the amount of the vertical displacement of the features of the specimen that can be tolerated without the loss of focus. So this depth of field, it can be given by the mu lambda over the square of the numerical aperture. The depth of field in optical microscope is very short, and it is in the range of the few microns, even less than it is the even 100 microns. So even this depth of focus is the range of image plane positions at which the image can be viewed without the appearing the out of focus. So higher the numerical aperture, we have the deeper the depth of focus. Yeah. Now actually, see, suppose actual samples like this. Suppose I have the pancake, which is the 12 mm thickness, and this is around the 100 mm diameter, and these are the bigger parts or components. Okay, so directly I cannot see these microstructures. I mean, by keeping the under microscope, I can see microstructure. So these parts or components, they have to be cut. Okay, suppose if the bigger components will cut with the bands or the EDM cutting machines. Suppose if it is a smaller samples, we'll cut with the isomers and all. Okay, and then after cutting the sample, so these samples should be mounted. This sample should be mounted. So using the sample mounting machine we have here, and actually we use the bakelite powder, which is the thermosetting plastic material. So these are the operating. So what is the temperature and pressure, and then so autocooling will take place. So after the mounting the specimen, so we have the different mounts of different size of the mounts, where this is a 1 inch, 1.5 inch, and the 2 inch mounts. So after mounting, so this has to carried out for polishing, and this first we'll do the rough polishing, and then so these samples are polished on the emery papers. If you see that, so from here to here, actually there is a increase in the fineness. So this paper, the coarse paper, okay, which is consists of the silicon carbide particles, which are larger in size. So as the number is increasing, so you will get the finer micron silicon carbide particles. So this silicon carbide particles, whatever they're on the emery paper, so it should be hard, and also it should have the sharp corners in order to cut the in order to remove the material from the specimen. And after polishing on the emery papers, okay, now we'll polish on the cloth. So okay, so this cloth actually will put the different types of the diamond paste, like 9 micron, 3 micron, and 0.5 micron diamond paste, and we'll put on that, and again we'll polish it. So this is for the ferrous material. If you want to go for the non-ferrous, like actually up to polishing is same up to this emery papers, and we have different class for the non-ferrous materials, and using alumina, so we can polish the samples. Now after polishing the samples, so after polishing the sample, we need to etch in order to reveal the microstructure details. So some of the etchants I have given here, where so suppose let us say this is a Keller's etch. So with this composition, we can use it for aluminum alloys in order to etch that. And suppose we have the Kroll's reagent, okay, so where you have the nitric acid, water, and SF. So for the titanium alloys, so like that, so you can use the picrol and aqua regia and nitrile all for the steels. And so actually for some of the different materials used for different agents are listed here, so you can go through. So now after etching the sample, okay, so I need to observe the what type of microstructures are present. So you can see that, so I will keep under the microscope, and microstructure which can be displayed on the computer screen, where actually suppose I have done for the T853 titanium, 5 aluminum, 5 moly, 5 and 3 chromium, where you can see the very nice beta grains. Okay, and also we can determine the grain size using the line intercept method. So which is the total length of the line, so divided by the number of grains intersected by it. Okay, And also we can determine the percent of the phase analysis. Suppose if you see this Ta6L4V, suppose we have the primary alpha, this one in a matrix of the lambda alpha beta matrix. So we can determine the volume fraction of these two. And also this is the aluminum silicon alloy, where you can see that, so this exhibits the presence of the aluminum alpha dendrites in a aluminum silicate eclectic. So depending upon the this material, so what type of material, what microstructure it consists of, whether it is in the cast from, rod from, or process, rolled, forged, and suppose if it is unetched steel, suppose any presence of inclusions are present. So all kind of information so we can get. So actually we can also use the different modes of observation in optical microscope, where so we have the these types of modes are there. One is a bright field, dark field, and phase contrast, polarized light microscopy, and differential contrast microscopy. So bright field and all, you can see that, so how it looks like. Okay, this, even though the microstructure is same, depending upon the mode of observation, you can see the features differently. So here you can see that which features bright field of view with the illuminated reflected illumination, and the dark field, whatever you are seeing bright there, so it will be looks as a dark. So these kind of dark field microstructures are very good to identify the cracks and the fits present in the material. And also phase contrast microscope. Suppose you have the specimen, irregular specimen kind of thing, so there you can use the phase contrast, this one. And also difference interface contrast microscopy. So this is mainly used for the wherever the surface topography is there. So in that cases, so you can use the differential interface contrast microscopy mode. So now actually I'm talking optical microscope, which resolution is around only 500 nanometer. And also with the latest object lenses, it can go up to 200 nanometer. But actually, if I want to see the finer detail, which are the less than 200 nanometers, then I can go to scanning electron microscope. If further details are required, I can go to TEM. So in the scanning electron microscope, so this is the schematic of the SEM, and the TEM is present. It is shown on this slide, where you can see that in a scanning electron microscopy, that means scanning means, so the beam of electron is moved over the specimen surface in a sequence of closely spaced lines. So actually on the specimen, this electron beam is moved closely, line by line over the area of the interest. So when these outer electrons are interacting with the specimen, so we'll get the different kind of the features. Suppose we'll get the urgent electrons, secondary electron, so on the backside electron, and also characteristic X-rays. So the secondary electron can be used for the fractalography studies, and backscatter electrons we can use for the microstructural studies. So we'll get the microstructure based on the atomic number contrast. This secondary electron, actually when the outer electrons are interacting with the inner electron which are in the specimen, outer electrons have sufficient energy to knock out this secondary electron. So these are the secondary electron from the specimen itself. But backscatter electron, actually some of the outer electron, they will interact with the nucleus of the atom, and then it will come out. So these are the backscatter electron which is used for the fractalography. So, and also in that process, actually we'll also get the characteristics X-rays. Based on the characteristics X-ray energy, we'll also determine the elements, what type of elements are there, and depending upon the number of counts entering in the counter, so it gives the quantification. So the resolution of SEM is around the 10 nanometers. Even so, with the latest advanced technologies and latest SEM, even we can go to up to 3 nanometer. So now actually I'm talking about the characteristics X-rays. So actually these X-rays are, if we see that, so it will be released. So when the difference in energy between the outer shell and the inner shell emits as a characteristics X-ray. If we see that this is the electron transition of an atom, you have the nucleus here, you have the K shell, this is the so the K shell and L shell, M shell, and the N shell. So what will happen that when you have the sufficient kinetic energy with your electron, so it will remove the electron in the K shell, and then it will be filled by the L shell electron. So now that energy is in the form of the characteristic X-ray. If it is from the L shell, we'll call that is the K alpha. And if the electron from the M shell, it is filled in the K shell, then it is called the K beta. So like that, we'll get the K alpha, K beta, and L alpha, L beta. And in this process, we'll get this is called the characteristics K alpha and K beta, because this is called the characteristics because of the it has the definite wavelength of the target metal used. Yeah. Okay. Now actually, I'm showing here this is the periodic table of the elements along with the X-ray energy. Where if we see that in this, suppose I have the iron. So where you can see the atomic number, atomic weight. This is the density, and also you have the energy, K alpha energy of that particular this one, and also L alpha X-ray energies are there. So now how I am using these energies to identify the elements present in my material. So now I will explain you. Yeah. So suppose I have got this is the EDS pattern. This is called the energy dispersive EDS pattern, and which is the intensity versus the energy in the kilo electron volt. So now I have the Fe K alpha and the nickel K alpha. These are the K alpha line. If you see that, as I mentioned, suppose if you see the nickel, where this is the atomic number, atomic weight, and this is the density of, and this is the energy K alpha energy and L alpha energy. If you see the nickel K alpha energy, this is the 7.48. You see that this is here. So like that, I can identify that this is the nickel. And also at the lower energy also, I can get the same element because the L alpha, nickel L alpha energy is very low. This is 0.84. So here also, I can see that this is the nickel peak. And also I have indexed the iron. If you see that what is the iron K alpha energy, this is around 6.4. And also you can see that this is the iron. And also L alpha energy is very less, 0.7. So this is one more example where actually EDS pattern, if you see that actually, yeah. So this one, if you see, already I explained you iron and nickel. Okay, now I'm going to chromium. If you see the chromium, so where it is present, so somewhere it is here, it is present. If you see the chromium, that K alpha is the 5.4 kilo electron. This energy is kilo electron. So you can see the 5.4 somewhere is here, and also L alpha is so 0.5. So somewhere here in this range. And also I have the titanium. So if you see the titanium K alpha energy, this is the 4.5. So you can see that this is in between 4 and 5. So this is around the 4.5, and L alpha energy also I'll get. And also like that, you can see the silicon. So if you see the silicon, so if you see the silicon energy, where you can see here, so this is the 1.74 kilo electron volt. So that you can see here. So okay, like that, so you can identify the based on the X-ray energy, so you can identify the what type of elements are present in your material or in your LI. And also suppose how many X-rays are entering in the counter, so that will give the how much quantification of your particular element. Yeah. So okay, now actually I have explained the optical and SEM and under TEM. Okay, now I'm going to TEM. If you see that what is the need of actually, so I mentioned that in the SEM, you can go up to 3 nanometer of the resolution. Suppose if you want to see the further down, okay, further down. So now I have to go to the transmission electron microscopy, where actually the illumination of the beam of electron with a wavelength of very fine, even 0.05 angstroms. So that means the wavelength should be, I mean, theoretically, so equal to the resolution of the material. And this electron microscope has much better resolution power, and it can show details up to so as small as the 10 angstroms or less. And electron microscope also provides the facilities for the selected area diffraction. That means actually in the small crystals which are in the nano size range. So from there also you can get the SAD pattern or diffraction pattern along with the microstructure. And basically in this, so we have the condenser lenses, objective lenses, and which produces the first magnified image, and it is further magnified by the intermediate lenses, and finally it is magnified by the projector lenses. So this is the basically TM is a massive instrument. So many these are there. So like condenser, objective, and projector lenses, and which produces the image on the fluorescence scheme. So we have the different modes in the TM, like bright field, dark field, and SAED. And bright field means, so you'll get the bright field image by taking the transmitted transmitted electron beam, and dark field actually by taking the diffracted beam. And also this is a selected electron diffraction pattern, where you will get the diffraction pattern from the very fine nanoparticles, okay, and along with the crystal structure. So as per this de Broglie, he proposed one equation that this lambda, so it should be equal to the root of 150 by applied voltage. So this lambda should be an angstrom. So at 100 kilo volts, if you see that lambda is around the 0.0387 angstrom units. So as I mentioned, the resolution of TM is less than 1 nanometer. Even up to you can go 0.3 nanometers. And the application of TM, so I will explain in the subsequent of my slide. Okay, now I'm going to the EPMA, so which is the electron probe microanalyzer EPMA technique. Basically, actually EPMA is a microchemical characterization techniques where you will get the elements and the quantification amounts of the elements from a small sized particles. So using the wavelength dispersive spectroscopy. So in SEM, I mentioned that identification of the metal based on the X-ray energy. Here, identification of materials based on the wavelength of the X-rays. Okay, so the photograph of the EPMA, so it is shown here where you have the some kind of electron gun, and we have the CCD camera and kind of things. We have the spectrometers. Okay, and then these are for the monitor for the optical images, and also this is for the electron images, and also this is the monitor. We can see the whatever the mounts you are keeping inside. So suppose if you don't know what is the, suppose you are keeping the actually 4 mounts and which sample you are there. So even you can see on the monitor, so which is the sample 1, 2, 3, 4 all. So actually, what is the information we can get from EPMA? So you can use the electron images, which is the BSc and the secondary images. And basically, both qualitative analysis and quantitative analysis we can do from the electron probe microanalyzer. So where in qualitative analysis, from the WL spectrum, wavelength this spectrum, you can find out the approximate identification of an unknown material, and also the elements in the sample area, identify, determine the angle at which Bragg is satisfied. Especially in the EPMA, the Bragg is involved, but whereas in SEM EDS, so this Bragg is not involved. Actually, in the X-ray dot mapping, we can see the elemental distribution maps over an area, so in the 2-dimensional, and also it is more suitable for the sample where degree of non-homogeneity of the distribution is adequate, and which shows the enrichment of the enrichments and depletion wherever that particular element is enriched or depleted. So that also we can see. And also in the line scan recording, so you can see the elemental concentration profiles. Okay, and also it shows how an element is varying along a line and vertical deflections of the line. So all this we can see. These all are part of the like qualitative analysis, and also quantitative also we can determine. So where actually it is carried out by collecting X-ray intensity from both sample and from standards, and obtain the K ratio and apply the, it is called a JAB correction, which is the atomic number contrast, observational contrast, and the fluorescence contrast. So corrections and to get the absolute concentration of the elements. Yeah. So actually, what is the sample preparation for EPMA? So this sample must be mounted with backlight powder, and it should be preferably 1 inch diameter and 4 to 13 mm in height, and it should be polished and free from polishing pit scratches, and it should be ultrasonically clean, and sample should be in unenriched condition. So actually, whatever the sample we are preparing for the optical, actually same sample you can use for the SEM, EPMA, and also one more technique is there, EBSD. For the TEM, actually sample preparation is different. So these are the applications of the EPMA where you can know the identification of the unknown materials. And also actually it is very important that you can study the chemical composition on the micron scale, okay, at phase boundaries and surfaces and at the grain boundaries. And also suppose diffusible couple interfaces and joints and the similar and the dissimilar metal joint. Even in the welded joints, actually this technique is very useful. Suppose you have the dissimilar metals are there. So if you are joined, then how that elemental distribution is there across the weld joint. So that also we can study using the EPMA. And also, in fact, identification of the influence and phases, and also so coatings also identify. So these are the limitations of EPMA. So elements below beryllium so cannot be analyzed, like you cannot detect the hydrogen, helium, and lithium. And these are the elements, light elements. So when in solid solution, it can be detected only when their concentration exceeds 3 to 5.8%. And also for the minimum particle size per quantity is around the 5 microns. For the qualitative analysis is around the 0.5 microns. And also price surface you cannot analyze using the EPMA. So that you can do using the scanning electron microscope. And this X-ray measurement is time consuming in WS, and the thin film and particles less than 0.2 micron size are difficult to analyze using the EPMA. Now just I want to compare the WS which is in EPMA and EDS which is in SEM. So very clear that so the elements determined by the wavelength, X-ray wavelengths are very accurate compared to the X-ray energy, because this is the high spectral resolution in the WS we can get, and in the SEM, so EDS, you will get the low spectral resolution. So this is around 150 electron volt. So there it is a overlap of the peaks will results in the improper quantification of the elements. And in this WDS, the specimens whatever you are using, it must be flat and in focus condition. And in the WDS, we have some moving mechanical parts. So in SCM, there are no moving mechanical parts and all. So in these currents are in the nanoamps we can use, and SCM we can use up to picoamps. And this is the detection limit. So up to 100 ppm of the particular element can be determined using the EPMA. And where in SCM you should be at least 1000 ppm. Yeah. Okay. Now just I will explain. So how I have used this EPMA. Okay. Whatever I'm talking, line scan, elemental mapping, and all. If you see that actually this is the micrograph I have taken. You can see that these are the elongated lines. So I don't know what are these black elongated particles you can see here. When I'm doing EPMA, when my electron beam is passing through this, actually whenever it comes here, that means actually these outer electrons, whatever I'm sending source, okay, the electron, the interacts of the electrons of this particular phase, and then we'll get the characteristics X-rays. Okay, so that X-rays, you can see that it is showing that, so this particular part, this whatever I'm showing here, this one is enriched with the manganese and the sulfur. So where you can see that this particle width is around the 10 to 12 micron. So you can see clearly that this particle is mainly consist of the manganese and the sulfur. So you can also see that elemental mapping. If you see that this is the also BS image. So same thing, whatever I have shown here, this is by line scan. And also if you see these particles, and also here you see the brightness. So wherever the manganese is there in this particle, it shows the high brightness here, and also sulfur, it shows the brightness in the particular particles, elongated particles. So which indicates that this is also this enriched with the manganese and the sulfur. So I have also confirmed this is particles are manganese sulfide by line scan, EPMA, and also using the elemental mapping. So one other application is, suppose I have the coating. So you can see you can see the bright contrast here. So this is actually some coating is there, which is around the 10 micron. You can see that. So here, when I'm moving my electron beam from this direction to this direction, you can see that on the bright face, you see that this is the blue line. So which is consist of the cadmium. Once that electron beam moves towards the gray contrast, you can see that this is mostly the iron. So this means that actually some kind of cadmium coating is given on the steel part or iron part. Okay, so in order to get the protection from the corrosion and all. So like this, you can do some kind of a particle analysis, coating analysis, and also in the weld joints and all, you can do the elemental analysis across the weld joint. So these are the application of the EPMA equipment. So actually, so far, actually, I have talked about the microscopes. Okay, so microscopes, these are called the direct imaging techniques. So which covers the small area. But whereas actually, so these are the indirect techniques, which are the X-ray diffraction and small and wide angle X-ray scattering techniques. So these are for the structural characterization. Okay, so basically this X-ray diffraction equipment we have purchased from the Proto Manufacturing Limited Canada, and this is from the Antwerp, Austria, small and wide angle X-ray scattering. So from the XRD, so basically it is like a crystal structure determination. From the XRD, we can identify the phases and also crystal structures. So all material falls under the 7 crystal structure systems, which are the cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and the triclinic. And also we have the 14 braces lattice and 32 point group. Under 230 we have the space groups. And also I can determine the measurement of lattice parameters very precisely, and I can measure the grain size or the crystallite size. So this we can get from the fluid, the top maximum intensity. I will also explain. And also texture we can get. So preponderation of the grains in a polycrystalline material, and also order disorder transformation. So this one also we can do. So we can get some extra peaks on the X-ray diffraction, so which are called the superlattice lines. And also we can determine the phase diagrams. So basically from XRD, it is indirect technique which give the at particular temperature what is the crystal structure phase and all we can identify from the XRD. So basically this XRD is a characterization tool on the atomic scale, whereas small angle X-ray scattering, so which is on the nanoscale. So we can determine the particles size, shape, distribution in the size range of the nano range, where you can determine up to 100 nanometers. You can also determine the particle shape, whether they are the cylindrical shape or the spherical, cylindrical, or lamellar kind of things. So we can determine the kind of the particle shape, and also so we can determine the precipitates in the heat rate sample which are in the nano range, and we can also find out the electron density profiles and also surface to volume distribution of the spherical particles. See, now I'll give you the introduction to X-rays. These X-rays were discovered by a German physicist called the Röntgen in 1895. Okay, so actually that time the nature of these rays were unknown. So because of that, they have given the name X-rays, and these X-rays are invisible, and it travels in a straight line. So it affects the photographic film. So the depth of penetration of X-rays are more compared to the light. Okay, so because of the discoveries of X-rays, so in 1901, so the Röntgen was honored with Nobel Prize for Physics, and in 1995, the German posted a stamp and dedicated to the Röntgen. So actually, the phenomena of actually X-ray diffraction by crystals. Okay, they were discovered by the father and son, which is the Henry Bragg and the William Lawrence Bragg. So they have got Nobel Prize in 1915 actually for the so these and they also discovered the characteristics X-rays which they are used to determine the crystal structure of the materials by X-ray diffraction. So these two father and son actually they have derived the simple law, which is the Bragg's law, which is the n lambda is equal to 2d sin theta. The n is the order of reflection and lambda is the wavelength of the target metal used. Generally, so we have the copper K alpha, which is having the 1.5406 angstroms length, and d is the interplanar spacing, and theta is the incident angle. And basically, in order to satisfy the Bragg's law, so you should have a regular arrangement of the atoms, and it assumes the average structure from the Bragg peak positions and intensities. Suppose actually where in these calculations and all, because lambda is known, okay, and theta will be measured, and we are calculating the d. If d is known, we can calculate the lattice parameter small a. And the wavelength of X-rays, especially, so these are useful in the diffraction in the order of 0.5 to 2.5 angstroms. Suppose if the wavelength is more, so it will be observed. So we cannot use it for the X-ray diffraction experiment. So mostly it will be in the order of for diffractional studies, it should be in the order of the 0.5 to 2.5 angstrom. So now I will explain you. So what is the information we are getting from the X-ray for diffraction? So if you see the X-ray peaks, okay, some of them are high intensity, some of them are low intensity. So these have some this called peak position. So on the X scale, you can see that this is the 2 theta you can see here. So if you see that actually, if you see the peak position, okay, this one in terms of the degrees and intensity in terms of the count. Okay, so now suppose this peak position will be determined by the size and shape of the unit cells, and also intensity, number of counts, how many counts are coming from the plane. It will be determined by the atoms in a unit cell. So now, so you can determine the crystal structure and what type of phases are there. And suppose if you know the full width at half maximum, okay, so you can determine the crystallite or the grain size. Okay, so crystallite size using the Scherrer formula or the Williamson method, Williamson Hall method. So where you can determine the both crystallite size and also presence of the strain in the material. And also if you see the quantitative phase also we can do. So suppose if the two phases are there, by seeing I can tell that this beta phase high intensity, so this is the it has the high volume fraction in that particular alloy, and alpha is the low fraction. So basically the X-ray intensity is directly proportional to the volume fraction of the pages present in the material. Suppose if you see that this is for the crystalline metal. So in case of the amorphous metal, where you can get the broad hump. So because amorphous materials do not have a long range periodicity, because atoms are scattered, and because of that, suppose when X-rays are falling on amorphous metal, they will be scattered over some angular range. So because of that, so you will get the broad peak. Even analysis of this peak will give the average interatomic distance between the atoms, and also how many atoms are close to the neighboring atom. So that kind of information also we can get from the amorphous. One more thing is we can also determine the residual stresses from the X-ray peak. So residual stresses, what will happen that, So because of the lot of strain, so basically it is a indirect measurement. So residual stresses, actually we can calculate from the change in the d values, because it shifts the peak position either left or the right, depending upon whether you have the tensile or the compressive stresses on the material. So now actually I will explain you so how I'm doing the phase analysis. Suppose I have identified that already this is the alpha titanium and beta titanium, but suppose if I don't know, so then I have to identify the this XRD pattern. What I have to do that, so this peak positions, so this peak positions, so I have to tabulate all the what is the 2 theta values, okay, in a tabular form along with this intensities and all. So after that, actually suppose in alpha titanium, you see that this is around the 30, if you see the 2 theta, this is the standard cards, okay, this is the ICD data, that is international center for the crystal international center for the diffraction data, where actually in the standard cards, so you have the 2 theta values, where suppose alpha titanium, so okay, my 2 theta is around 35.17, where you can see that, so this is 30, this is 40, so where this is the 35, so that means that this is the alpha peak. So where see if you see the next peak position of alpha titanium, it will come around the 38. So if you see this 38, so if you see here, this is the 40, so actually somewhere here you have the alpha. And like that, suppose at the 40 also, so at the 40, if you see that at 40 also you got the alpha rating. So okay, like that, so you can say that actually these peaks are belongs to whatever the 30, whatever the peaks they are there at the 35, 38, 40 and 53, so they belongs to the alpha titanium. Suppose for the beta titanium, so if you see that those peaks actually, so this is comes around 38 and the 55. So you see that, so this is around here the 38, and also it comes around the 55 highest intensity. You can see here it shows that, okay, here, and also 69 you can get the beta phase. So okay, like that you can identify, so using the standard cards, okay, you can identify so what type of phase is present in your XRD pattern, okay. Yeah, so actually, as I mentioned that, so by using XRD, we can also do the quantification of that particular elements, okay, so our phases so present in the material, where the whatever the counts or intensity is directly proportional to the volume fraction of the phases present in the material. Okay, so here I am putting, this is the tungsten, which are 5 hours milled powder, and this microstructure parameters of the this 5 hours milled tungsten is given here. So by using the Williamson Hall method, so I have derived all these things, and the average lattice strain is around 0.24%, and the average crystallite size, so this is around 45.6 nanometers. And when I gone from 5 hours milling to the 20 hours milling, so the crystallite size has reduced to 28.8 nanometer from the 45.6 nanometer, where in the 5 hours milled powder it is around 45.6 nanometer, but in case of the 20 hours it is around the 28.8 nanometers. And also the volume fraction of this spacer, if you see that the weight fraction of tungsten is 80.2%. So these all highest intensity peaks are belongs to tungsten, and tungsten carbide phase, so whatever the small peaks are there, these peaks so belongs to tungsten carbide, and the tungsten carbide has the volume fraction of the around the 19.8%. Yeah, so now just I will explain. I mentioned that XRD is a characterization technique on the atomic scale, but now I'm going to small angle X-ray scattering technique, so which is the characterization tool on the nanoscale. So basically this is the analytical method to determine the structure of the particle systems, that means particle size, shape, distribution, so that should be within the 1 to 100 nanometer range. And also, so and also the what type of what are the different shape of the particles, like we have the spherical particles, laminar particles, or globular particles, cylinder kind of particles, that also we can get from the small angle X scattering. As I mentioned, small angle, so that the 2 theta is very 0.12 up to 5 degree. So the basic principle in the axis, this scattering pattern is a Fourier transform of the particle distance distribution function, which gives an inverse relationship between the particle size and scattering angle. So if your scattering angle is low, so you will get the bigger size particles. Okay, so in the especially in the small angle X-ray scattering, we'll talk about the actual form factor. So but in case of the X-ray diffraction, we'll talk about the structure factor. So structure factor will come whenever the particles are very close. Okay, like atomic arrangement, the atoms in the metals and all, so there you can get the structure factor, but form factor will result whenever the particles are actually far away from each other. So now I will explain in detail in my next slide. And so this is the formula. So where in the X-ray diffraction formula is Bragg's law, n lambda is equal to 2d sin theta. Where in the small angle X-ray scattering, where q is equal to 4 pi sin theta by lambda, where q is the length of the scattering vector, and so this is theta is the scattering angle, and lambda is the wavelength of the target. We are also used here. It is the copper K alpha, and q length of the scattering vector, where you can see this. So this is the vector. It is shown here. And actually, so as I mentioned that, so we can determine the powder particles in the nano range. Suppose if the particles are in the nano range, they are chemically highly reactive, and then it forms the agglomeration. In order to prevent the agglomeration, so we keep the particles, nanopowder particles, in some kind of the solutions. It may be acetone or the glycerol or some kind of the solutions, where the particle, it should not interact with the chemical this kind of solution. And then whatever the particles are there, it will be subject to some kind of the ultrasonic vibrations, where these particles will be it will prevent the agglomeration basically. And then after getting that solution, with the help of the syringe, we'll keep the quartz tube, where you can see the quartz tube here, and then it will put for the in the sacks, this one using the sacks. So we analyze what is the particle size, shape, distribution. So all we can do using the sacks. And also suppose you have this kind of the fibers. So basically, so these fibers, what is the thickness of the layers? Suppose within the fiber, suppose if you have the layers, how many layers are there? What is the distance between each layer, and what is the thickness of the layer? So all the details we can be obtained from the small angle X-ray scattering. Yeah. Okay. Now actually, so this is the tungsten powder which is milled for 100 hours. Okay, so to analyze the 100 hours milled tungsten powder, so I have used all three equipments. One is the X-ray diffraction, small angle X-ray scattering, and also I have used the transmission microscopy. Where if you see that, so from XRD, so actually from the full width at top maximum intensity from the X-ray peak. Okay, so using that and all, using the Williamson-Hall method, I can get the crystallite size. Okay, so here I can get the crystallite size here. Are the slope from the slope I can get the strain in the particular material. So basically, if you see that Williamson-Hall method, this is the beta cos theta equal to eta sin theta plus 0.9 lambda by d, which is like the y is equal to mx plus c. Okay, so beta cos theta is on y-axis, and this is the slope, and sin theta is on x-axis. So this d is the crystallite size. So actually from the X-ray diffraction, so from the particles. Okay, so I calculated the grain size is crystallite size grain size around 14 nanometers, and the lattice strain present is so 0.32% is present from the small angle. So you can see that see, this is the curve of scattering curve. So what you get from the small angle X-ray scattering. So from this we can obtain the phase distance distribution function. You can see that here. So this is the phase distribution function with respect to the R. So this is in the nano range, where from this graph, I have measured that you can see that this dia is where it will go here around 18 nanometers, and length is around the 44 nanometers. And these dimensions, whatever I got the actual SACS results, these are confirmed with the transmission. So this is the bright field micrograph, where you can see these particles. As I mentioned that from the SACS, it is a cylindrical shape. And also, so dimensions are, so this width, this one is around 18 nanometer, and this length is around the 44 nanometer, you can see, and this is the 50 nanometer scale. So you can compare. So using all three techniques, so okay, X-ray diffraction, you can determine the crystallite size. Using small angle X-ray scattering, so what type of what are the particle sizes and shapes, and TM also will give the size and shape of the particles. So okay, like this, so we can characterize the nanopowders using the all three kind of the equipments. Yeah, suppose I have the small angle X-ray scattering and XRD. Suppose I have the particles like this, where outer is it consists of mainly the some kind of the amorphous polymer, and inside we have the crystal structures. So actually from the XRD we can get the crystal structures, and suppose from outer or from the sacs we can get the some kind of the amorphous polymer kind of the surface on the outer. So using this you can get the both the features using sacs and XRD. Yeah, so now I have talked about the microstructure characterization techniques, and also I have talked about the structural characterization techniques. Okay, now just I will present the hardness testers. So where you have the macro and the micro hardness testers. So this is the universal hardness tester where it consists of the Brenner, Rockwell, and Vickers. You can see that this Brenner hardness also you can get this Brenner hardness number. So this is the load divided by the surface area of indentation, where this P is the whatever the applied load should in kg, and D if you see that this is the capital D, that is the diameter of the ball, and small d is there, so that is the diameter of the indentation. Okay, so by knowing all this, so you can measure the subrenal hardness number of that particular material, and also we can use the Vickers hardness number. So okay, this is also defined by the load divided by the surface area of indentation, where this VHN is 1.85 P. So this is the load divided by the average length of the diagonals. This is L, average length of the diagonals in mm. So using this formula, so we can also determine the Vickers hardness number. Okay, by selecting the different loads. So that load will be depending on the material. So Rockwell hardness test also, where actually this utilizes the depth of indentation under constant load, and which gives the hardness. And we have these are all on the macro hardness. We'll get the bulk hardness. Okay, and micro hardness test also we have Vickers and the no hardness testers, where we can use the load in terms of the grams. Okay, so these micro hardness tests will be useful. Okay, to find out the individual hardness hardness of the grains, or the hardness of the coating or the plated material. Suppose any carbonizing is there, so actually that also we can measure using the micro hardness testers. Yeah, so now actually I have explained you all microstructural structural characterization technique. So now actually I want to present so how I am using those characterization techniques in research and development activities. One such example, so I will present you how I have established structure property costing correlations in metastable analysis. So okay, mainly so actually TA253, so which is a latest addition to the family of the metastable beta analysis. You can see that this is the titanium, 5 aluminum, 5 moly, 5 Nd, and the 3 chromium, and also similar molybdenum equivalent alloys. Okay, so basically, so these applications, whatever that TA253 or the TA5L, 5L, 5N, 3 chromium, these actually they are using in the landing gear assemblies of the aircraft. You can see that actually, so this is the aircraft. Okay, it is not completely shown here, but this is the landing gear. You can see that. So these alloys mainly they are using in the landing gear assembly of the aircraft. If you see the clear picture here, so this landing gear, so if you see the clear picture here, so this actually bogie beam is there. So in the landing gear, you have the bogie beam there. You can replace the steels even by the titanium TA253, and also you have the some kind of the these parts are there, where whatever I have shown here, these all are replaced by the actual titanium. So mainly because in order to reduce the weight of the aircraft. Okay, so actually thereby your actual fuel consumption will be decreased. Yeah, but now I'll give you an introduction to actually titanium alloys. Okay, these titanium alloys can be classified as alpha, near alpha, alpha plus beta, metastable beta, and beta, depending upon the amount of allying elements and volume fraction of the beta phase. These high temperature BCC, which is having the body centered cubic crystal structure, this can be retained in metastable beta condition at room temperature by adding the large amount of these beta stabilizing elements. And this beta can be aged to form very fine alpha precipitates, which are the hexagonal system SCP in a matrix of the beta. The strength of these alloys are mainly depending upon the size, shape, distribution, and volume fraction of the alpha precipitates in the beta matrix. And these alloys, especially metastable beta titanium alloys, have the high strength and also very good hardenability. So because of the good hardenability, so you can fabricate the larger components, and a number of applications of these alloys are evolving for structural components, such as what I mentioned in my previous slide, basically landing gear assembly in the aircraft industry. Yeah, so actually, even though the alpha plus beta titanium alloy, so this is the actually TA6L actually 4V. So which is the Ti64. This is the mostly used in aerospace industry. Even actually, whatever the titanium produced, 80% of the titanium produced is used in the aerospace industry. Among that 80%, so the TA6L4 is the 50% it occupies. So this is the importance of this alloy in the aerospace industry. Some of the parts, okay, they are fabricated from the TA6L4V. So even though, so the uses of more of this particular alloy Ta6L4V. But in the last 10 to 15 years, the use of metastable beta titanium alloys, so it has grown in the aerospace industry. So because they will possess the high strength, very good fatigue properties, very good better hardenability, and also good fracture toughness, all it possesses. And these alloys actually they will not transform to martensite upon room temperature, so which results in the only metastable beta phase. And this alpha phase can be precipitated from the metastable beta phase upon aging, what I mentioned there. And these can be processed at lower temperature than the alpha beta alloys. So these are actually some of the metastable beta titanium alloys, where actually, as I mentioned, that alloy Ta1253, it is the latest addition to the family of the metastable beta titanium alloys. This alloy has been derived from the another alloy, it is a Russian alloy VT22 to replace. Actually, the alloy Ta1253 is developed from this one VT22 to replace the alloy 1023 in the landing gear assemblies of the aircraft. So if you see that actually the landing gear assemblies of the aircraft, actually first they started with the Ta6L4V, and then they have gone to Ta6L sequence to this one, and then 1023, 10 2 and 3L, and finally now they are using the actually Ta553. Actually, the reason is mainly increasing the strength levels. So if you see that actually Boeing, so and Airbus, so those these both are the manufacturer of the aircraft. So yeah, if you see that, so every time, actually every day, if you see that, you are seeing the bigger aircrafts and all. So where it carries the more number of passenger. Suppose in order to so thereby it is increasing the load. So in order to withstand that load, so you should select a material which is having the high strength in order to withstand the loads and all. Now basically what I mentioned that the Li-Ta253, okay, it is developed to replace the Li-1023. If you see the actually because of these properties, if you see the if you see the UTS YS, okay, where these are their tensile properties, you can see these are the better than the 10-3, and also toughness is more compared to this alloy. And also actually if you see that in order to get these properties, the Li-Ta253, it has to be air cooling. So, but it has to be the water quenching. So air cooling means, so air cooling, with the air cooling, you will not get any cracks and all. And with water quenching, so if increasing the thickness of the component, so you'll get the distortion and the cracking. So because of the air cooling, so you can make the components or parts up to 6 inch. So which is the 150 mm thicker component you can make. Yeah. So now I'll present the flow chart of the experimental work plan. So as I mentioned that this is the Ta253. Okay, so already it is available in the literature, and also other 3 alloys. So I have designed from this alloy by keeping the molybdenum equivalent constant with different combinations of. So I have not changed the alloying elements. I have changed the amount of alloying element. Suppose in this we have the 5 moly. So I have reduced up to 3.5 moly, and vanadium is increased up to 7.2 vanadium. So like that in the third alloy, if you see that aluminum moly I kept constant, I changed the vanadium and chromium. So in the fourth alloy, if you see that, so there is a change in the chromium and moly. So like this, so I have designed these alloys from this alloy by keeping the molybdenum equivalent constant. Okay, and these all 4 alloys they are produced in the form of the as cast. Okay, in about the fan cakes, I will explain. And also these as cast alloys are beta solution treated, and then it has done the water quenching, and I have carried out the microstructure and phase analysis and hardness, and I have also carried out the aging studies. Okay, I will explain in details. And also these cast alloys are forged in alpha beta phase field, and also subject to the rolling in alpha beta phase field, and then evaluate the microstructure and the tensile properties. So I'm not covering these things, all these things in this presentation, only up to the forging and the rolling. So the microstructures and the tensile properties. So actually, if you see that these all 4 alloys, whatever I explained earlier, you see, so these are designated as A1, A2, A3, A4. And also I want to tell you that, so by keeping the molybdenum equivalent constant, which is the 8.15, so if you see that this is the constant, so this is calculated from the molybdenum equivalent. Here we have the formula molybdenum plus 0.6 vanadium, and also 0.4 tungsten, and 1.6 you can see the chromium here, and also it should be aluminum. Okay, 1 into aluminum we can see here. And also I calculated the beta transistor temperatures using the formula, this one. And also actually these for the making the alloys, this one. So I have selected the raw material like this, the titanium sponge, moly, aluminum master alloys, and vanadium master alloy, and the aluminum shards, and the chromium pellets. This all after taking the charge. Okay, these are these raw materials are melted by using the non-consumer vacuum arc melting. And initially, these raw materials were blended and kept in a water-cooled copper crucible under a vacuum of the 10⁻³ millibar. And this copper crucible is filled with an argon gas, and then the arc between the thorium tungsten electrode and the charge can be struck, and then melting begins after the stable arc is established. So we do the 4 times melting in order to get the homogeneity. See, actually, so whatever I'm talking about the allying elements like aluminum, moly, vanadium, and chromium. So what is the role of these alloys? If you see that aluminum is the alpha stabilizer, which increases the beta transition temperature, and moly, vanadium, and chromium, these are the beta stabilizers. And if you see the molychromium, these are the slow diffusers, which inhibits the microscopic quartering. Thereby, you can get the highest strength values, and vanadium increase the yield strength. So by adding this sufficient amount of moly, vanadium, and chromium, the transference temperature is reduced to below the room temperature, such that the beta is completely retained at the room temperature. So these are the samples we have selected for the chemical composition. Okay, so how we are determined, I will explain. So we have the ICP OES for the elemental analysis, and for interstitial elements, we use the Lico gas analyzer. So for the chemical analysis, elemental analysis, the metal is in the form of the turnings, and for the interstitial elements, it is in the form of the cubes. Yeah. So now I have presented the nominal composition, so which is we have proposed, and this is the analyzed chemical composition, which we have analyzed using the ICP-OES, and also these elements ICP-OES, and also you can see the interstitial elements we have observed here. So this analyzed composition is very close to the nominal composition. As I mentioned that actually these all the 4 alloys, okay, they are produced in the form of the pancake, which is a thickness of the 12 mm, and this is 100 mm the diameter. So where actually you can see that this is the beta transverse temperature, where you have calculated using this Electron formula, and also this is the theoretically, and this is determined using the difference scanning of calorimeter DSC, okay, where you can see that these are very close. And I have carried out the forging and the hot rolling at beta transverse -25°C, where for the LiA1, let us say this transverse is 850. So then I have to do the beta transverse -25°C, where it comes 825. And for the LiA2, it comes around 793, A3 it comes around 795, and A4 it is around the 839°C. Yeah. So these are the microstructure, optical microstructure of all the 4 alloys in the cast condition. If you see that average grain structure of if you see the LiA1 is the 580 micron, and whereas in average grain size of the A2 is 1100 micron. Okay. And this A3, so this is around 276 micron, and this is around 750. So if you see that the grain size of A1 and A3 are the final, I mean, compared to this A2 and A4. And this also we have also I have also presented here the XRD patterns of all the 4 alloys in the cast condition, where it shows the presence of the beta and alpha phases. Okay, and so these alloys also display strong texture in as cast condition. That actual texture part is I'm not going to present in this talk. Yeah. So now actually, as I mentioned that, so we have also studied the aging studies in all the 4 alloys using the 4 different temperatures like 300, 400, 500, and the 600°C, and also different time intervals like 15 minutes, 30 minutes, 60 minutes, 120 minutes, and the 240 minutes. So if you see that actually, so after carrying out the aging treatments, so the specimens are characterized using the XRD, optical SCM and TM, and also we have measured the hardness values. So if you see that actually these are the XRD pattern of all the 4 alloys, which are raised at the 300°C for the different time intervals like 15 minutes, 30 minutes, 60, 120, and the 240 minutes. So in case of LiA1, see that from 15 minutes to up to 240 minutes. So it exhibits the presence of the omega and the beta phases. So where this omega will come from in the quenching itself, which is called the other omega. But in case of LiA2, if you see that after 60 minutes of the aging, so I'm seeing the alpha phase in this. So and also with increasing the time, this alpha phase is increasing, volume fraction of the alpha phase is increasing, where you can see that this LiA2, it shows the presence of the omega, alpha, and the beta phase. So in case of A3, even from 15 minutes to up to 240 minutes. So I have seen only two phases like omega and beta. But in case of Li A2, even I have got the alpha phase precipitates, okay, after 120 minutes. So it is clearly seen in the 240 minutes of the age specimen. So actually that means that actually if you see that A1 and A3, so there are no alpha phase peaks, but A2, A4 only we have got the alpha phase peaks, because mainly it indicates that the presence of alpha phase in A2, A4 is okay, mainly due to the, so the molybdenum content is very less in this. So that is only 3.5 moly, and which is the strong beta stabilizer. So because of the low moly content, the beta phase in this is not stable. So there is for the alpha phase precipitates forming in this. Now actually I have also confirmed the formation of those alpha phase precipitates by taking the hardness values. So where you can see that, you can see the hardness values, the hardness versus the aging time I have plotted here. From this is about 15 minutes, 30 minutes, and 60 2 hours, and the 4 hours, 240 minutes, 4 hours, where you can see that maximum hardness we observed for the A2 and A4. You can see the here. So this is for A2 and this is A4. So that is mainly because of the formation of the very fine alpha precipitates at the 300 degrees centigrade. 300 degrees centigrade aging temperature. But whereas in A1 and A3, this hardness is very less compared to this one. But when I gone for the 400 degrees centigrade, okay, the alpha is started forming in all the 4 LIs. Okay, and whatever the alpha has formed at the 300 in the A2 and A4, so it might have grown. And in case of A2 and A4, if we see that the hardness is less, so compared to the LI, A1 LI. So in A1 and A3 LIs, because hardness is started forming at the 400 degrees centigrade. So the volume fraction of the alpha phase increases, increasing aging in temperature and time. So this also reflected in the increasing in the hardness values. Yeah. So as I mentioned, so earlier I have also explained the TEM application of TEM, like bright field, dark field, and the selected diffraction pattern we can take like that. I also mentioned. Now actually I'll give some I'll give some example with this explanation. So I have carried out the TEM studies of for LI A1 and A2, which are aged at 400 degrees centigrade for the 4 hours. So these are the bright field image. Okay, bright field image, where you can see the you can see that these are the alpha layers, very fine, and they are evenly distributed in the beta matrix. And these are like alpha and alpha 2. We have the two variants which are perpendicular, which are oriented at 90 degrees to each other. And here, so this is the selected area diffraction pattern. So we have taken from the 011 zone x, beta zone axis. And in case of LI A2, whatever the actual fine and even distribution of alpha layers observed in LI A1, but in LI A2 we got the patches of the alpha layers. So and also clusters of the alpha layers. So within the cluster, the alpha layers are parallel to each other. So here also you can see the alpha and alpha 2. See, the presence of the clusters or the patches of alpha layers are okay mainly due to the similarly oriented omega particles, which I have shown at the 300 XRD pattern. So because of that similarly oriented omega particles, so it might have grown in the same direction. So because of that, we got the clusters of alpha layers in LIA2. So here if you see that, so there is a small difference in the amounts of aligning elements results in the variation in the microstructures. So this is the zone axis we have taken from the bright field image. And I have so these are the SCM microstructures of the LIs aged at 500 degrees centigrade for the 60 minutes, where actually it exhibits the presence of the, you can see the grain boundary alpha, islands of alpha, okay, and also sub boundary alpha. So and basically, so this grain boundary alpha, so it forms. So you can see the alpha precipitates along the grain boundary. So because of these grain boundaries possess the high energy, and also solid concentration is okay, more at the grain boundaries. So you can get this grain boundary alpha. And also islands of alpha. What are the patches I have seen in the TEM? So in that big, so in the SM, so I'm not able to see. So these are the like island of alpha. So these are mainly because of the multiple site nucleation initiated by the similarly oriented omega particles, and also actually subboundary alpha. So these are in the form of the curves. So these might have formed okay, mainly because of the actual strain associated with beta 2 alpha phase, because lattice parameters of beta and alpha are the different. So mainly because of that, so this it might have formed like subboundary alphas. And at the 600 degrees centigrade, okay, aging treatment, you can see that whatever the fine precipitates are formed here, so it has grown and it has formed the Whitman structure. So the LI1 is still, it is finer, and A2 is the, you can see the coarse alpha layers, it is a Whitman structure. So even though the molecule length is same, which is 8.15, but actually the different amounts of aligning elements resulted in the different microstructures. You can see this one, and also whatever the layers, whatever the layers here. So you can see that these layers, actually phases of the layers, it also acts as a nucleation sites for the another alpha phase, which is called the secondary alpha. So this is the E-based microstructure. So which is, you can see that this whatever the alpha you are seeing layers here. So these are the different colors because it shows the different orientations. So because of the different orientations, you can see the different colors so of the alpha layers. And in this, especially in case of LIA1, so we have re-established the orientation relationship, which are called the Burgers orientation relationship between the alpha and the beta matrix. If you see in the fold figures, this is taken from alpha layer and taken from the BCC matrix, and you can see the location of the poles here. So it all are matching. So which indicates that so it is following the orientation relationship, which is the so this is the SCP 001 alpha parallel to 110 beta plane. This is the closed packed plane in the BCC, and this is in SCP. And closed back direction 112.0 in alpha is parallel to the 1111 beta. So this is the closed back direction in the BCC. Yeah. So now I'll present the microstructure and mechanical properties of all the 4 alloys, which are forged up to 20% reduction in null plus beta phase field, and also unidirectionally hot rolled in null plus beta phase field at a temperature of the beta transform 25 degrees centigrade. So actually pancakes of the 4 alloys were hot rolled with different reductions like 30%, 50%, and 70% for the microstructure studies. And the pancakes of 4 LS were directly hot rolled, 70% reduction for mechanical properties anisotropy. So you can see that this is the unidirectional rolling, and this is the direction of the rolling. So whatever I said, this is the alpha plus beta phase field. So where you can see that this is the region in this, and these are the sample selection, how I selected for XRD, optical microscope, and then EBSD and all. Yeah, so actually these are the photographs of the forging and the rolling mill, these photographs. And if you see, this is the forging, and this is from the we are purchased from England. The capacity of the this one is the 1 ton capacity okay, ram weight, and maximum intake we can take 300 mm height into 200 mm square round, and minimum finish size is around 10 mm thick. So it is then in the rolling, so we have purchased this from the Germany. So capacity is 100 ton. Okay, you can see maximum intake size is around 30 mm thick, 150 mm width, and we can go we can roll up to the 1 mm thickness. Yeah, so you can see that these are the photographs of the photographs of these are the in the as-cast condition how I have got. And you see this is the after giving the 20% acrylic forging, and then this is after the 70% hard rolling. So you can see this one photographs. Yeah, so okay, now actually I'll present the microstructures of the hard roll. So of the all 4 alloys which are hard rolled in null plus beta phase field with different amount of reduction, like 30%, 50%, and the 70% rolling reduction. And suppose if we see for the LI1 from 30% hot roll to 70% hot roll, if you see this actually, so there is a systematic variation in the grain size, and with increasing the reduction from 30 to 70%. Okay, so you can see that actually the whatever the equax kind of grains here, so you can see the elongated grains. So that means that the aspect ratio of the grains are increasing from 30% to 70%, and very fine grains you can see globular grains or recursive grains, which are the recursive grains. And magnification of this microstructure also actually shows the presence of the ingrained shear bands, so which forms because of the non-uniform deposition in that particular grain, and it also indicates the plastic instability. So actually, if you see in LIA2, actually the microstructure is entirely different. So it is showing the banded microstructure, where you can see that high magnification optical optical image. You can see them very fine globular alpha, and also some elongated alpha splits are there. So this is okay mainly because इसमें the molecular content is low. So in this case, the molecular content is more, and because of the low molecular content, so there is a large one fraction of the alpha splits in this LI. And because of this, you see in this I'm seeing the equatorial grains, and here I'm not able to see any grains, equatorial grains, mainly because this amount of amount of actually fine alpha loss, it might have it might have prevented the formation of the recrystal grains in LiA2. And A3 we can see the elongated grains, and A4 if we see high magnification, it is exhibiting the combination of the microstructure of the LiA1, okay, where you can see the Indian shear band kind of thing, and also very fine alpha precipitates which are observed in case of the LiA2. So actually it is the E-based analysis, E-based microstructure analysis of the for the LI A1 and A2, which are 70% hot rolled. So if you see that here I'm showing the grain boundary map. Actually here you can see that. So they have the three types of the grain boundaries. You can see the grain, you can see the green, sorry, blue and the red. If you see that, if you see the 2 to 10 degree, so this angle is misorientation angle is 2 to 10 degree for green, 10 to 15 degree for red, and greater than 15 degree blue. So if you see the LiA1, so this is the 2 to 10 degree, okay, and 10 to 15 degree in case of LiA1, so they belongs to the Indian shear band. Suppose greater than 15 degree, so as I mentioned, if you see the small recrystal grains, so those are the recrystal grains. So in this case, in LiA2, so 2 to 10 degree, so these are the subgrains. Yeah. So okay, now I'll present the mechanical properties of all the 4 LIs, which are hot rolled up to 70% unidirectional hot rolled. Okay, where if you see that actually, so this is the 70% hot roll hot roll sample. So you have the rolling direction 45 degrees RD and the TD. So okay, now actually I have cut the samples in the rolling direction and 45 degrees the RD direction and the TD direction, actually tensile samples. Okay, and then these tensile samples were subject to tensile test at a room temperature at the strain rate of 10⁻³ per second. So in all the 3 sample direction I did for all the 4 LIs, where from the engineering stress strain curves I have derived this yield strength UTS and all elongation. If you see that among all the 4 LIs, LiA4 exhibit the highest strength values, and whereas LiA3 shows the among all the 4 LIs, it is the values are very less. If you see here, and the strength values of A1 and A2 are in between these two. And also, so ductility of LiA3 is maximum. You can see up to 21% we have got, and also if you see, we also calculate the in-plane anisotropy properties where the LiA1 is maximum, and also this in-plane anisotropy for LiA3 is the minimum. So actually, even though the molybdenum equivalent is same, so there is a variation in the mechanical properties, mainly because of the different amounts of the alloying elements. So here in LiA4, actually chromium is highest. So because of the highest weight fraction of chromium, so we got the highest yield strength and the UTS values among these all 4 LIs. Yeah. Okay. Now actually, I will explain you. So this is a tensile flow behavior. Tensile behavior of all the polars in the 3 different sample direction. So this is the on the y-axis. You can see the true stress versus the true plastic strain, which are on the log scale. So these points I have got from the engineering stress strain curve, where it is converted into the true stress and the true strain using the engineering stress is true stress is engineering stress into 1 plus E, which is the strain. Okay, strain. And also true plastic strain, so ln 1 plus E, okay, 1 plus engineering strain. So actually these all points are in between the yield strength and the UTS regions, where actually these all curves are fitted with the strain hardening equations, okay, like aluminum equation, Ludwig and Swift and Ludwigson equation, in order to obtain the any value. This is the strain hardening exponent value. Actually that is very important in order to study the formability of the material. So because of this, actually we have fitted all this curve in order to obtain the small n value. And also the fracture surface of the tensile test samples exhibits the presence of the, you can see the flat features and also ductile dimples, and the fraction of ductile dimples are decreasing from RD to TD. Yeah. And also this work hardening behavior, actually I have shown here. So these are the curves. So this work hardening rate, okay, which is the d sigma d epsilon curves, it have been generated by the numerical differentiating the true stress with respect to the two plastic strain values, where you can see that these curves, suppose in the RD, so in the RD direction, suppose this is the stage 1, stage 2 and the stage 3. So like that I have identified this stage 1 is associated with the elastoplastic transition, and stage 2 is the multiple slip activities, and 3, so dynamic recovery starts after the sufficient pile up of the dislocation. So in all, I identified what are the stages are there with the different directions and how the it is involved in the relate to the microstructural parameters and all. Yeah. So now actually I'm showing one XRD pattern on the E-based microstructure. The reason is actually it is reported that generally in metastable beta titan alloys, the plastic deformation mechanisms are so dislocation control strain handling and followed by the formation of the orthorhombic martensite and also formation of the twins and the twin dislocation and the dislocation interaction. So in order to confirm that any formation of the orthorhombic martensite, okay, I have carried out the XRD, but I have not identified any orthorhombic martensite axial peaks in XRD, and EBSD we have not identified the any twins. But actually what we observed that on the surface of the tensile test specimen, so we observed the presence of the slip. This indicates that okay, dislocation control strain handling occurs in all the three stages of the cell in order condition, and slip is the predominant deformation mechanism during the tensile testing. Yeah, so actually this is also EBSD analysis where I want to show you that. So suppose this you see that this is the blue, what are the blue, it is a recrystalline refraction, and yellow it is substructure, and the red is a deform. In case of the blue volume fraction, so which are the recrystallized, so in case of LiA1 is more and LiA2 is less, and deformed and substructure are the deformed structure, so in A2 is more. So okay, like this, so the okay, large fraction of recrystalline fraction in LiA1 is so more compared to the A2. So A2, because of the this alpha precipitate, it will not allow the beta grains to form the recrystallization. Yeah, actually I will conclude that particular talk of the structure property process population of the alloy, this one, and also other three alloys. Okay, and we also studied the development of alpha phase, which is investigated in all the four alloys as a function of the aging temperatures and time intervals. And the fine and even distribution of alpha phase in beta matrix exhibits either uniform distribution of alpha alloys with two variants or patches of the parallel alpha alloys. And the microstructure of alloys A1, A3, and A4 exhibits the recovered recrystallized and ingrained shear bands. And LiA2 displays the only presence of large fraction of subgrains. LiA4 displays maximum strength, and A3 exhibits the minimum strength. The ductility is maximum in A3 and it is minimum in A4. So both the tensile flow and workout behavior have been explained, studied, and slip is the predominant decoy mechanism during the tensile testing of the all four beta titanium alloys. Now I will explain you. So how I have used the this characterization techniques. So in metallurgical failure analysis to find out the cause for actual failure. So this is one component. This is the bevel gear which we have received from the Hindustan Aeronautical Limited. Okay. So to find out the cause for the damage, I will show you. So this is the failed bevel gear of aero engine. Now I will characterize and I will find out some results. Based on the results, I concluded that it has failed by the decarburation. Yeah. Okay, now before that, actually, I will explain you. Actually, I'm talking about the failure. So what is the failure? So when a part or device can no longer perform its intended function, so the part has failed. Basically, we'll do the failure analysis. Actually, basically, it is a scientific and systematic analysis carried out in order to pinpoint the cause of failure and suggesting remedial measures to minimize the occurrence of such a failure in the future. And actually, if you see what are the steps any engineer you should know, what are the steps involved in manufacture of the engineering or structural component. Initially, first we design. Okay, so we'll do some drawing, dimension, factor safety. After design, depending upon the application, we'll select the material, whether it's high temperature or low temperature, what is the purpose this material. And also we have to do fabrication, because whatever the material is there, so we have to do some processing, heat treatment and machining or welding in order to make the component from the material. And then we'll do the basically quality control. Okay, and then we'll assemble, and after assembly also we have to do the maintenance. Why I'm explaining all these are anyone deficiency of this may cause the failure of that particular component. Now, what are the sources of failure? Whatever I explained earlier, suppose any deficiency in design, it may lead to failure, and the deficiency in the selection of material. So for high temperature application, you cannot select the material which can withstand the low temperatures. Suppose any imperfection in the materials, like any defects are there, segregations, inclusions, that, and also deficiency in processing and errors and improper service conditions. And what is the impact of failure analysis on society? Because cost of failure analysis, and then improvement of the product. Now, just I will explain you what are different stages. So basically, we have to collect the background data. What is the manufacturing history, service history, photography, and also inventory of parts, abnormal condition. What are the conditions are there? And preliminary examination, visual examination is very important actually. And this also will do the detailed photography of all parts. We'll do the non-destructive tests. It may be the dye penetrant or X-ray radiography, ultrasonic test, and the magnification depending upon the requirement. And we'll do some mechanical test if required, hardness, tensile, impact test, fracture toughness, fatigue, or this kind of thing. And also sample selection is very important in failure analysis. And also microscopy examination. Suppose, as I mentioned, that stereo microscope, it determine the origin of failure, determine the direction of crack growth. Suppose beach marks are there. Suppose you can say that it is by failed. It is failed by the fatigue. Suppose we have the chevron patterns. So it is a failure. And determine the ductile or brittle fracture load. And metallography and microscope, suppose we can know class of metal by metallography and microscope examination, whether it is in the cast or the rod product, what is the failure mode. So we'll do chemical analysis, we'll do analysis, and then we'll do some recommendations. So now actually, so I'm talking about the gear. So just I'll give some introduction. These engineering components such as ball bearing, gears, bushings, and gun barrels. So these actually they are surface hardened by chemical heat treatment to obtain the properties in the core and surface differently. So in some cases where your surface should be hardened wear resistance, and also core should be it should be the ductile and tougher. So where actually such a combination of properties ensure that component has sufficient wear resistance to give long service life, and also at the same time it should have the sufficient toughness to withstand the shock loads. And in order to get these kind of the difference in the microstructures are hardened various and the toughness, we do the case carbonizing, which is the most widely used process for surface hardening of steels. And the microstructure basically it is a high carbon tempered martensite, written arsenate, and the carbides. Yeah, so if you see that actually basically these gears are the tooth reveals that work in tandem with another gear to transmit the power or the motion to change speed under the direction of motion. Basically, this gear system are usually classified according to the orientation and arrangement of its associated rotational axis. And these are the parallel shaft gears, intersecting shaft gears, and non-parallel intersecting shaft gears. So this actually bevel gear, what I'm talking, so this belongs to intersecting shaft gear. These types of gears are used to carry the greater loads. So if you see the photographs of the gear, bevel gear in the different views, if you see that actually it consists of the 31 teeth, 31 teeth, and also this gear teeth removals are not observed in this photograph. But if you see, this is the close view photographs where you can see that these actually some of the teeth they are not damaged, but some of the teeth actually you can see the damage on the teeth. So where you can see the damage on teeth. So these if you see that this damage on the teeth. And next actually we have determined the chemical composition of the damaged teeth, which is called the worn out, and also undamaged teeth, which is we call the normal. So if you see the chemical basically it is iron based, and with the allying elements like silicon, vanadium, chromium, manganese, nickel, these are there. Okay, but if you see that the composition of the damaged and undamaged, so both are same, so there are no deviation in the chemical composition. And as I mentioned that this is the stereo microscope of the teeth. So on the teeth surface, if you see that so closely, I have looked at. So we have observed the some kind of the micro cracks here. So you can see the micro cracks. So formation of these micro cracks, it indicates that actually, so this is not that much hard on the surface. And we have also analyzed the microstructures. Okay, microstructures. Actually, if you see the teeth, these are single teeth. So we have cut cross-sectionally like this. And we have selected the total out of the 31 teeth, actually 4 teeth normal which are not damaged, and 4 teeth which are damaged teeth. So after the cutting of these teeth, we are mounted, polished, and etched, where you can see that. So these are the 4 teeth. They are designated as ABCD, and another these are the designated EFGH. You can see this one, and this is the normal teeth, where you can see that this is the dark. So actually that, as I mentioned earlier, these the teeth actually they do the carburizing. So you can see that this is carburizing. So before that also you can see that, so it's not look like in the it's not the dark. So that means what? So it is not carburized means even though it might have carburized, but during the during the heat treatment, so the carbon might have removed from the surface. So because of this you are seeing that it is not the dark. And here you can see the metal removal, whatever I showed there now. So you can see the metal removal on the teeth surface. If you see the microstructure in clear, if you see that at the top of the top edge of the teeth. So you have the some kind of precipitates. So which are, some of them are fine and some of them are coarse, and also the shape of the precipitates are varying and the size are also varying. And if you see the side edges, so you have the fine precipitates on both the sides compared to top edges, and there is a formation of the crack. But at the center, it is mainly the tempered martensite. Yeah. So here, so also, so you can see that this is the optical microstructure of the worn out teeth, that means damaged teeth. So again, so you can see that there is a variation in the microstructures on the top edge, on the side edges, and basically at the center it is the tempered martensite. Yeah. And if you see the optical microstructure of the normal teeth, so this is basically the which is the material has not come out from the surface of the teeth. But here problem is that, but also which are normal, which are undamaged, it might have resulted in the damaged condition. Okay, now this is the SC microstructure of EDS analysis, where you can see from the very fine precipitates, from the very fine precipitates and all. So you can get the EDS pattern. So actually already I explained so how to index the EDS pattern, how to identify the element. But this particular precipitate is enriched with the niobium, vanadium, and the carbon. And also, as I mentioned that, so at the top edge, some of them are very coarse and some of them are very fine. This one. So these are the coarse. These are the gray contrast particles. So which is enriched with the carbon, vanadium, and chromium. Whereas this, you see the small, the fine precipitates, and they are enriched with the carbon, tungsten, and the chromium. And if you see from the carbonizing, from the core to interior, from the carbonizing to core to interior, there is a variation in the microstructures. You can see this is the decarbonized layer. So very fine precipitates, very coarse, and the fine precipitates. And at the here also tempered martensite, which is the very fine precipitates and all, it is there. Now actually we have also measured the micro-hardness profiles on all the 8 teeth, 4 normal and the 4 damaged teeth across the gate teeth, where you can see that actually the specified hardness is, it should be a 700 VHN. So this is the specified for this gates and all. Okay, but here you can see that actually some of the teeth, okay, the hardness values are it is below the 700 VHN. So actually that indicates that actually the hardness is not sufficient on the surface of the gate teeth. So because of the low hardness, the cracks might have started from the surface of the teeth and resulted in the removal of the material. And in the fractography studies, so we have not got any fracture details because rubbing has taken place, but only these micro cracks. So as I mentioned that the formation of the cracks because of the low hardness, because of the decarbonation, okay, so it might have removed from the surface of the gate teeth. Yeah, so actually we have also measured the residual stress measurement on the teeth. Okay, so in this direction we have selected the 4 locations, and also so other here also, so we have done the 4 locations. You can see using the X-ray diffraction technique with the chromium alpha lambda 2.291 at a Bragg angle of 150/60, this one for the 2-1-1 plane. If you see that actually whatever the stresses I have measured all are in the compression nature only. So there is no problem of the residual stress in this, but only problem is this particular gear has damage mainly because of the decarbonation, because of the low hardness. Yeah, so now actually these are the findings. Okay, the chemical composition of the both gears, damaged and damaged, both are same. And the cut piece after mounting, okay, it displays the presence of the decarbonized layer, and this might have occurred decarbonization during the heat treatment. Okay, and the edges at the top edge, mainly it shows the presence of the coarse precipitates. At the side edges, the precipitates are very fine. And microstructure at the center of the teeth, it shows mainly the tempered martensite. And also, as I mentioned, so we got the 2 types of precipitates. One precipitate is enriched with the chromium and carbon, and the other is the chromium tungsten, okay, carbide. And actually, as I mentioned, there is a lot of variation in the micro-hardness values due to presence of the decarbonized at the top and also carbohydrate layer, and also presence of the return aspects on carbide. And the decarbohydrate layer in all the teeth might have formed during the heat treatment after the carbon treated. So as per the specification, the hardness of the carbohydrate layer so should be more than the 700 HV, but it is falling after measuring the hardness. We came to know that the hardness is less than the 700 HV, which has resulted in the damage of the surface of the gate teeth. And this surface of the gate teeth is softened due to depletion of carbon in the matrix, and this has resulted in the worn out of material. So there are compressive stresses were observed on the gate teeth, which is good for compressive is always good. And the worn out of material on the surface of the bevel gate teeth has therefore occurred due to the decarbonization layer. Yeah. Okay. Now I'll conclude my talk. Okay, so the material has worn out from the surface of the bevel gate teeth due to formation of the decarb layer at the surfaces, and the micro cracks have originated from the edges, top and side edges of the gate teeth, and propagated inside, and then resulted in the worn out of the material. So as I mentioned that, so we'll find the cause for the failure, and also we'll give the remedial measures. Okay, so that to minimize the such kind of a failure in the future. So the remedial measures are: the component may be heated in the controlled atmosphere or in vacuum, and the decarbonated surface layer may be removed by machining after the heat treatment, and coating may be applied to the components prior to the heat treatment. So actually, yeah. So I would like to acknowledge DRDO for financial support, and Dr. G. Madhusudan Reddy, Director DML, for his kind encouragement. And I would like to thank members of the ACG, TEG, STG, EMG, MBG, DSG, MW, MEG, SFC groups of DML for their provision of external facilities. And also thank you very much so actually for giving me opportunity to present in this program. And actually and also I will show you so these are the references. Okay, so some people, if they are interested, they can go through these references. Okay, thank you very much, madam.
Sir, thank you, sir.
Yeah, so if any questions are there, you can ask.
Dear participants, if you have any questions, please ask. You can even type your question in chat box.
Yeah.
You have covered a number of areas, sir.
Yeah,
it was
thank
very
you.
interesting lecture, sir.
Yeah.
You have given the basics of material characterization. You have talked about the metastable beta alloys and even the failure analysis, how it is done. A lot of information you have shared, sir. Thank you so much.
Okay, thank you very much, madam.
Any questions, dear participants? Anyone? This is lunch time.
Oh, okay, madam. So yeah, madam, once again, so thank you very much for madam, and also Saraswati madam and Padmalata madam, so for giving me an opportunity to present my work in this program. Okay, thank you, madam.
Sir, thank you so much. Thank you.
I'm leaving now.
Yes, sir. Thank you, sir.
Yeah, thank you very much. Thank you.